So remember, one of the things that we know about vectors is vectors have direction and magnitude. And let's kind of talk through this conceptually a little bit. So if I'm traveling in a circle, so we're going to prepare ourselves for later in the semester. I'm traveling in a circle, and I am traveling at a constant speed. Now remember, speed is a magnitude. My speed is a magnitude. So anywhere on this vector or on this circle, if I'm here, I'm going to have a velocity vector that's headed in that direction, but it has a magnitude, and we'll give it a magnitude of 2. I'm right here, I'm heading in this direction, it's going to have a magnitude of 2. And I'm over here and I'm headed in this direction, it still has a magnitude of 2. And I'm over here and it has a magnitude of 2. But in each of these cases, I'm in a different direction. So my velocity is in a different direction. And so as I'm traveling around this circle, I am going to have an acceleration. We're going to play with this vector here. So I'm going to put this vector red because this is one of the things I want to look at. So there's my red vector. And we can actually represent this vector in a couple of ways. We're going to give it an angle, and I'm going to give that an angle of 60 degrees. So we have that angle there. It still has a magnitude of 2 meters per second, but it's going to come off in that direction because we're going to look at that vector specifically. So if I'm traveling at a constant speed around this circle, I'm still going to have an acceleration. And I have an acceleration because I have a change in direction. And that's what's giving me my acceleration. Because remember, my acceleration is a change in velocity with respect to time. And my velocity is a vector, and I can either be changing in direction or I can be changing in magnitude. I can be doing one or the other. What we're going to find later is that this change in direction is going to give me a center-seeking acceleration, which we're going to end up calling a centripetal acceleration, and we're going to see that a little later. But I wanted to get this idea that going back to our vectors and understanding our vectors, I've got magnitudes not changing, but direction is changing, and that's going to result in a change in vector, and a result in an acceleration. So we're going to look at this vector, and we're going to examine this vector. So I've got that vector, and I've got it at 2 meters per second. And we've said that that's at 60 degrees from our horizontal. Now, in chapters 1 and 2, we've also looked at, this could be written as, if I want to know this point, I can go from my polar coordinates. My polar coordinates would be written as r and theta. So I could rewrite this as 2, and my theta is 60 degrees. But if I want to know what this point is, right, I can break this up and use my trigonometry to get there. This is going to be x is going to equal my hypotenuse times the cosine of the angle. My y is going to equal the hypotenuse times the sine of the angle. And so I've got 2 sine of 60. And if I plug that in, I think that's going to be 1, if I remember right. Nope, I would have it backwards. 1.73. This one is going to be 2 cosine of 60. I knew one of them was going to be 1, and that's 1.00. So now I can write this in my Cartesian coordinates as 1.00 and 1.73. And that's in our XY coordinate system. So we did talk about changing coordinate systems. And this is what your algebra book talks about, but your algebra book never tells you that that is a vector. They never tell you that that is a vector. And so we've already worked problems that take our vectors. So I'm going to take my 2 meters per second vector, and we're going to show that that's a 60 degrees. And we're going to take it, imagine that we're walking, we're taking a trip, and I've walked across at 2 meters per second. I'm walking across the football field at 2 meters per second. And then I'm going to turn to catch the ball because that's my route. And I'm going to go ahead and make this 5 meters per second. And we want to know the resultant vector here as the crow flies. Now, the thing about vectors is that if I say my red pen is a vector, and I say my green pen is a vector, I can move these things and slide these things around mathematically however I want to. I can add this vector that way, okay? Or I could do it this way and I can get the same result. I can add vectors head to tail. And earlier we said, okay, let's write these vectors using our notation with an I, J, and a K. And this is a unit vector. These are unit vectors. And I is in the X direction. J is in the Y direction. And K is in the Z direction. So we could write those 2 vectors, and we've done this before. So this vector is easy. So we're going to call this vector A, and we're going to call this vector B. And vector A is easy because vector A has 0 component in the I direction, and it only has components in the J direction. So now I've written that vector in vector form. Now my vector B is going to be a little different. So I'm going to have a component that goes into the X direction, and I have a component that goes into the Y direction. My component in the X direction is going to be our 2 cosine of 60 degrees. And my component in the Y direction is 2 sine 60 degrees. And this is our vector B. And my vector B, which we've already figured out that this is 1.73 in the I direction. Nope, sorry, I got it backwards again. It's 1 in the I direction, and it's 1.73 in the J direction. And these are still in meters per second. So if I add A plus B, that's going to give me This is going to equal this vector that we have in our picture that's green. It's going to give me that green vector, which is my resultant vector. Gives me that resultant vector. I'm going to add my x components. 0 plus 1 is 1. I'm going to add my y components. I'm going to get 6.73. And I've got my vector components. Now, that tells me in my Cartesian coordinate systems, I'm at 1 and I'm at 6.73. And if I did that on my graph, just by moving our heads to tail, we know that that's correct. So drawing your picture is really, really going to help. But maybe I don't want it in this kind of configuration. Maybe I do want to have this angle and I want to know the magnitude. Well, the magnitude of my resultant vector, and I represent it mathematically by using that absolute value, is going to equal my a squared plus b squared is equal to c squared, but my a squared in this case is 1 squared plus my 6.73 squared. And if I do the square root of that, this gives me my 6.80 meters per second. That's the magnitude. That's the magnitude of my vector. My angle goes back to what we were talking on Friday. I've got to go back to my arc tangent because I'm going to look at the y side. Well, we know the y side is 6.73. And we know that the x side is 1. So that's going to give me my angle. I'm going to first make sure I'm teaching physics 2, and physics 2, I have to be in radians, and general physics 1, I have to be in degrees. So I got to make sure my calculator's in the right spot. And this gives me an angle of 81.5 degrees. So really what's about to happen to us as we move from 1 dimension to 2 dimensions, we're going to have to account for the fact that our vectors aren't just in a single dimension, that our vectors are actually moving through here, and we have to be able to look at our components. Because I think I showed you guys the idea of if I'm on a train and my train is moving, and we have an object and we've got a person that's tossing a ball. The person that's tossing the ball, and we're going to throw the ball up in an upward direction. This person sees the ball doing this. And then it comes back down. And that's the behavior in the y direction. So if I'm in the car and I'm tossing a ball, or I'm on a train and I'm tossing a ball, the y direction is going to look like that. But this ball is really moving, like we showed with the basketball on the lab, the actual path. So if I'm standing outside the train, the actual path that I see looks like this. But I have a velocity in the x direction. So I have a velocity in the x direction, but the key here is there's no acceleration. This one is going to go up and come right back down. And the only acceleration on this one is the acceleration due to gravity. And if we look at our equations of motion, this is the change in y is equal to our initial velocity in the y direction times time plus 1/2 my acceleration times time squared. And if I convert that into gravity, that's the way the y looks like. My change in x is my initial velocity in the x direction plus my acceleration times time. But in this case, we have no acceleration. So I'm just going to have an initial velocity in the y direction. But as we look at this curve here, what does my initial velocity look like? Think of it this way. I have a golf club. And my golf club is going to hit a ball off the tee at a certain angle. We're going to go ahead and say what that angle is. We're going to make that angle 40 degrees. And we're going to say, because we've got a camera or something that we've actually measured it, this golf ball is going to go off at 30 meters per second. So the magnitude is 30 meters. We've got the angle, because this is my golf ball. So your factoid of the day, there is no standard in a set of golf clubs. If I buy tailor-made golf clubs, or I buy Callaway golf clubs, or I buy whatever kind of golf clubs, a 1-iron isn't a 1-iron isn't a 1-iron. A Callaway 1-iron is going to be at a certain angle. At TaylorMade is going to be at a slightly different angle. The difference between my 1-irons and my 7-irons is that angle face, but there is no golf standard for the angle face. It's not like a standardized Major League Baseball. It's not like a standardized bat. Depending on what kind of golf clubs you have, that angle is going to be slightly different between each of the different brands. Just the factoid. I actually went and looked it up. There is no rule that all 3 irons have to be a certain angle. Just thought people would like to know. But as I have my golf club hitting my golf ball off the tee, and I get this, and I have those angles, what now is I'm going to have to figure out the velocity in the x direction, and I have to figure out the velocity in the y direction, because my x and y motions are independent. So I have to come up with this vector. So what that means is I need to write this vector that I now have in polar coordinates into a vector that looks like my individual component parts. I want to write my vector in that form. I'm going to want to write my vector in that form. So let's do that. So we're going to do this again. So now I have a vector, and we've said that this vector is 30 meters per second. We've said that that angle is 40 degrees. I'm going to have my component in the x direction. And I'm going to have my component in the y direction. And my x direction component is going to give me my velocity in the x direction is going to be my 30 meters per second cosine of my angle. And if we plug that in, I'm going to get 22.98 meters per second. My y component, which is going to give me my initial vector in the y direction, is going to be 30 meters per second. Sine of the angle and I'm going to have it be 19.28 meters per second. So I can write my velocity vector now as 22.98 in the I direction plus 19.28 in the J direction in meters per second. So we've got that set of vectors doing really well. Now, physics can be fun, as you guys have all figured out, but I can give you different kinds of coordinate systems. So let's look at a different vector. So we're going to give a different vector. Say what we're doing is we're on that cliff. This is our cliff. And we're going to throw a ball with an initial velocity. And we're going to throw that ball with an initial velocity of 16 meters per second. And we're going to give you this angle. And that angle is 25 degrees. We want to write it in vector notation. We want to write it in our vector notation. Well, here's my x component. Here's my y component. So my x component, which is going to be my v of x, that is going to be my 16 meters per second. But I've got the opposite angle here, not the adjacent. So I've got to do the sine of 25 degrees. So I'm going to end up with 6.76 meters per second. My x component or my y component is going to give me my v of y, except now that's 16 meters per second cosine of 25 degrees. And that's going to give me 14.50 meters per second. So now I can write it in my vector component form. .76 in the I direction plus 14.50 in the J direction, and that's in meters per second. So you have to be careful. You have to watch for the angle. And I just said that, and we got another problem. That's the magnitude. We have to take into account the direction, and that is a negative. It's going downward. So I have to account for direction. We have to watch the angle because that's going to give us direction. That just gave us magnitude. Because my direction is actually downward. So we have to make an account for that. So that's not quite correct until I put that negative in there, because this is the vector we want to represent. And drawing our picture is going to give us that particular aspect. So if we're just playing with vectors, I can give you a vector A. So I'm going to give you a vector A. And vector A is going to be 3.26 in the I direction minus 7.21 in the J direction. I'm going to give you a vector B that's represented by a 5.62, and my angle is going to be 145 degrees. I want to know what the resultant vector is. Well, I can rewrite my vector B in its form. I can do it mathematically, and I'm going to go ahead and do that. I'm going to get my 5.62 cosine of 145 degrees. And I'm going to have my 5.62 sine of 145 degrees. Oops, it's an I. And that's a J, so we got that right. So I'm going to do that. This is a negative 4.60. And this is a positive 3.22. So I can do it mathematically. I can add my A plus B. So I'm going to get my 3.26 plus a negative 4.60 in the I direction. And I'm going to get a negative 7.21 plus 3.22 in the J direction. This gives me a negative 1.34 in the I direction. And that's going to give me this is going to give me a negative 3.99 in the J direction. But let's plot this out and see what we're doing. So this first vector, my vector A, was a positive 326, but it was a negative 7. So my first vector looked like this. My second vector looked like this, because that's my 145 degrees. So my resultant vector is somewhere down here that looks like that. Nope, 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 nope. It's going to be down in here. Because I'm going to take my vectors and slide it head to tail. So if I did this with my pen, I have one vector that looks like this, and I have one vector that looks like that. I'm going to slide this vector head to tail, and I'm going to end up getting it down to there, and it's going to end up down in this quadrant somewhere. So drawing your picture also helps you to verify. And draw to verify, because I've got to add vectors head to tail. And we can do that a little differently. Let's play this picture a little differently. And it doesn't matter which vector I do first. So my first vector, we're going to do the 5.26 at 145 degrees. So it's going to look something like this. Then you can give yourself a new coordinate system. And now we can add that vector that was 3.2 and negative 7.1. And we can have it draw that looks something like that. And there is going to be your resultant vector. It's going to look something like that. So that's one way to do it. If I started with the other vector, okay, if I started with the other vector was down here along these lines. And then I give myself a coordinate point. We end up in that same area because I'm adding, there's head and there's tail. So I'm adding head to tail. Okay, I'm going to stop there today and we will start throwing